Okay.
Okay, guys, let's see what we got here. Hold on. Hey, let me call you back. I'm in class right now. All right, one of you had a question?
Yeah, that was it was for the test yesterday. So you said we were able to turn it in a little bit late, and when I did, it was closed. So I sent like the test through like Canvas email. Is that all right?
Yeah, I'll find it. There, I have a bunch of people like that.
Okay.
Oh,
yeah.
I'll find it.
Perfect. I was just making sure
I did the same thing. It was giving me an error when I was submitting it. It was actually before 8:30, and I couldn't submit it, so I emailed it to you through Canvas.
Okay. Yeah, I don't know. I'm no Canvas expert, so can't really say much there. All right.
Sending it to the email is okay though, right?
Yeah. I mean, I have a girl in the Math 30 class that she still hasn't been able to figure out how to submit things. She has them all sweaty going outside. Okay. So what'd you think of the exam?
7 was a joke that you created just to make everybody angry.
Did you see the pattern to the answer though?
Yeah, but it sucked.
It wasn't that bad once you saw.
Oh, it was horrible.
I kind of figured it was something to do with the powers where you multiply them, and then when I multiplied them to get rid of one of the cubes, I was like, well, if I do that, then I'm left with 12 cubed. Yeah.
So that's what I did. And then you go up, and I just divide till I get all the way down to the end, and then from there it's just an easy integral. I mean, but okay. Any other problems bother you?
10 was a little bit of pain.
Yeah, can we do 10 in class together?
10
Okay.
to play around. I don't know if there's a shorter way to do 10.
No, it's partial fractions. Okay, let me do this here. Turn this down. I've been in my car all day. I had to drive out to Murrieta, or what's down by Murrieta that starts with an M?
Menifee?
Menifee, that's right.
What do you have to do? What do you have to do over there?
Oh, I bought an e-bike, a mountain bike.
Oh, okay.
And I had to pick it up, and so anyway. All right, so here we go. Share the screen. Let's see. OneNote. Okay, this is from this morning. So we'll do this in text mode. So 185. Okay. So now I got to do this. Flip this fella over. And like so. And don't want that. Okay. Okay, so we've got here x cubed plus x minus 1 divided by x squared times x squared plus 1. Okay, so it's a proper fraction. The degree of the top is 3. The degree of the bottom is 4. So this would be the nugget piece that we'd be working on for partial fractions. Okay, so that means you equal a over x, b over x squared, cx plus d over x squared plus 1. And again, if you weren't tuned in that day, I can't really give you. Somebody turn the volume off. No. Go back up to here. Happens people log into class. Leave there. Okay. Now, should I just turn these guys off? All right, so I cross multiply the whole thing. And we're going to get x cubed plus x minus 1 equals ax times x squared plus 1 plus b x squared plus 1 plus cx plus d times x squared. Okay, so what I did.
Hey, I have a quick question. I noticed that you have the x squared at the back, but what did, oh, never mind. Sorry, I saw it. Just caught it. See it. Sorry about that.
Okay, so here's how I did it. I figured out everything that was going to multiply x cubed. There'd be an a plus a c. And then I looked at everything that would multiply an x squared. And it was going to be a b plus a d. Then I looked at everything that was going to multiply an x. And I got an a. And that's it. Okay. And then I multiplied everything that had a number, and that was just going to be the b. Okay, so if these two polynomials equal each other, a plus c has to equal 1, b plus d has to equal 0, a has to equal 1, b has to equal -1. Okay, so if that's the case, the c is now going to be 0, and the d is going to be a 1. So that means that the integral of x cubed plus x minus 1 over this x to the 4th plus x squared dx is equal to the integral of 1 over x plus -1 over x squared plus 1 over x squared plus 1. And so this ends up being log of x plus 1 over x plus tan inverse of x. Okay.
Wait, real quick. Out of those, I got how you got the natural log of x, because that's 1 over x. And then the plus 1 of x, is that the x squared one? And is the inverse tan because it's equal to the x squared plus 1?
Yep, the tan inverse of x came from that guy.
Okay.
When you integrate negative x to the -2,
Yeah.
you get -x to the -1 over -1, which is just going to be 1 over x.
Oh, okay. And then the inverse of tan, when you integrate, becomes, or when you integrate x squared plus 1, it becomes tan inverse.
1 over x squared plus 1.
Okay, 1 over x. Okay, thank you.
Okay. All right. so anyway, how about number 5? I haven't even looked at your exams yet, guys. I think they're going to take a long time to grade. You remember what happened on number 5? So you're going to integrate -1 to 1 dx.
It's divergent.
Well, f of x equals x cubed plus x. F of negative x equals 1 over negative x cubed minus x, which is -1 over x cubed plus x, which is negative f of x. So this says that f of x is odd. And the integral over a symmetric interval from -1, negative a to a will just be 0. Now it will cancel they will cancel themselves out in the limit if you do it, if you actually went and did improper, because it does go through 0. Okay, but it's one of those deals where it works out. Okay, number 1 was integration by parts. 2 was just like the problem Brian asked, and so I changed sine and cosine. 3, you just break off a sine and turn it into 1 minus cosine and let u be cosine x. 4 was pretty straightforward. Talked about 5. 6 was another integration by parts. 7 was the one you guys all hated. All right, so I'll look at these probably starting over the weekend and let you know. All right.
Hey, somebody just asked for number 5, is divergent the wrong answer then? Because it's 0 or divergent?
Well, let's see if it's actually divergent. Okay. So what
Hey,
I'm going to do
Professor.
here. Yeah.
So I just edited the PDF. So I used the computer to draw the answers on in the PDF and then turned it in. Is that okay?
Probably.
Okay, thank you.
So this guy, we will go from -1 to 0 of the f and plus the 0 to 1 of the f. Okay, now both of these are going to be improper because the f of x is 1 over x cubed plus x. Okay, so the integral from -1 to 0 of 1 over x cubed plus x dx plus the integral from 0 to 1 of dx over x cubed plus x. Okay, this is going to be the limit as epsilon goes to some kind of 0 of, okay, hold on a second. Look, I'm in class. Stop. Don't let the dog out. Okay, so here's where we have our problem. We're okay at -1. We're okay at 1, but 0. So if I was to go, epsilon goes to 0 through positive values, -1 to negative epsilon 1 over x cubed plus x dx. And don't tell Takasaki I'm doing this. No. This would be epsilon to 1, and then it's going to be the dx over the x cubed plus the x. Okay, now 1, let's partial fraction this up. 1 over x cubed plus x is x times x squared plus 1. So with partial fractions, a over x, and then plus bx plus c over x squared plus 1. Okay, so now if we cross multiply, 1 is going to equal a x squared plus 1 plus bx plus c times x. Okay, so if you let x equal 0, then a is equal to 1. Okay, so 1 is equal to x squared plus 1 plus bx squared cx. Okay, so there's no x, so the c is equal to 0. And the b, well, the b is going to have to be negative 1, I think. Let me do that again real fast. 1 equals a x squared plus 1. This pencil is way too sensitive. There's got to be a way I can fix that. Okay, so if I let x equal 0, then a is going to equal 1. Okay, and so 1 is going to equal to x squared plus 1 plus bx plus c times x. So 0 equals x squared plus bx squared cx. So a is 1, c is 0, and the b is negative 1. Okay, so I was right. So we'll get rid of all the evidence. All right, so this is going to be the 1 over x plus negative x over x squared plus 1, and nothing more. C ended up being 0. Okay, so now we need an antiderivative. So the antiderivative of this guy, integral of f, is going to be the natural log of x, and then u, the bottom, then it's going to be minus, let's see, integral negative x squared plus 1. So if I put a 2 and a 1/2 there, and I move that outside, minus 1/2 natural log of x squared plus 1, which maybe we can write as the natural log of x divided by the square root of x squared plus 1. Okay, so now what I'm going to do is I'm going to evaluate the natural log of x over the square root of x squared plus 1 at negative 1 and negative epsilon. Okay, so this is going to be negative. It's going to be the natural log move it up, it's easier. I'll scroll back down. Okay, so it's going to be the natural log of negative epsilon over the square root of epsilon squared plus 1 minus the natural log of negative 1 over the square root of 2. Okay? And when I evaluate the natural log, the antiderivative, x over the square root of x squared plus 1, now I'm going to go 1 and epsilon. This is going to be the natural log of 1 over the square root of 2 minus the natural log of epsilon over the square root of epsilon squared plus 1. Okay, so the limit I'm having trouble with my I haven't eaten really today. Dropped under 200 pounds. And not by like I'm forcing myself not to eat. I just forgot to eat today because I drive out to Menifee. Okay, so what we've got is the limit as epsilon goes to 0 through positive values of the natural log of x over radical x squared plus 1, negative 1, negative epsilon. Okay, and then it's going to be plus the natural log of x over the square root of x squared plus 1. This guy evaluated at 1 and the epsilon. Okay, and this is where Takasaki would be screaming and yelling. Okay, so for this, write down all 4 of these terms. Okay, it's the natural log of negative epsilon over the square root plus 1, okay, minus the natural log of negative 1 over radical 2, and then plus the natural log of 1 over radical 2 minus the natural log of epsilon over square root of epsilon squared plus 1. And again, the limit as epsilon goes to infinity. So I'm still working inside of that bracket. Okay, now here's where everything cancels. Remember that these are absolute values. So this is positive epsilon up there. And then again, that's going to be positive. Okay, and then plus the natural log of 1 over radical 2 minus the natural log epsilon. And this, my friends, these all cancel. So the limit as epsilon goes to 0 of all of those things is 0. Okay, So that means that our integral is equal to 0. So here's what's happening, guys. It's going off to infinity. Like if we just looked at like the 1 over x cubed guy, okay, it's going like this and like this. And so when we go from here to here, what we keep doing is we take a we start integrating here, like right here, and then we stop at some epsilon right there, and then the same thing here. And because the function is odd, all of this area cancels with all of this area. They're going to infinity at the same rate. When we get into chapter 11, we'll talk a little bit more about, how things are going to infinity. Now, you didn't have to do this for this problem. You could have just recognized that it was odd. All right. Okay, so I will be looking at those probably tomorrow night. And the new news is we are at the end of chapter 8. All we did was 8.1 and 8.2. Okay, now the other sections are interesting, but these are things that you guys could maybe read on your own. So Eduardo, the math major, and any other math or physics majors, let me just tell you what's happening in chapter 8. In 8.3, it's a physics problem, finding the center of mass and stuff like that. So if you're doing that, you might want to read that at your leisure. I don't test you on it. Center of mass is basically figuring out where to stick your finger under the book so when you hold it up in the air, it won't fall off. Okay. 8.4 was some econ and biology stuff. 8.5, this is mathematical statistics, so probability. If any of you are thinking about minoring math or minoring in statistics and are math majors, it's pretty much required at every university you take, a core. So mathematical statistics is always there. So this is kind of the beginnings of it. So you can kind of look at it in there and tell me what you think. Okay, so we will come back to chapter 9 later. All right.
I have a question, Bobby.
Yeah, what?
So, like, if you'll give us the next exam, and if you bring something from chapter 8, it will be only from 8.1 and 8.2.
Yeah. So to give you 10 questions, I'll give you some more integrals to do or something like that.
Okay.
Okay. Now the reason I'm coming back to chapter 9 later is it has to do with some chapter 11 stuff. Okay. So chapter 9 is the differential equation stuff, and we will, look at that at the end. We're kind of here at the end of week
3.
Yeah, week 3 out of 8. So,
Hey, Bobby, when's our next exam then? Because don't we have the traditional 5 plus a final?
yeah, so probably maybe on Tuesday, I'll post it out there.
Okay.
And maybe I'll time it, maybe not. I don't know. I'll definitely put a due date, but I'll give you, more time. This was pretty successful. I had 67 people turn the test in before 8:30. So And then a couple of you said that you had issues and you submitted it another way. So it looks like it all kind of worked. Okay, so in 10.1, we're going to start talking about what are called parametric equations. Okay, now we've actually done this stuff without you knowing it. If you guys remember, if you go back to pre-calculus with me, the way that we defined the trig functions is we had a unit circle. Now, you know how much pride I take in my circles, but I don't have any chance here because this Apple pen is just too squiggly. I do know that if I was in the other thing, the thing that Tyler and Debbie use, they can help you draw perfect stuff.
And next to your pens and pencils up in the corner, you have a shapes maker.
Oh, yeah?
Yeah.
Mm.
There you go.
Oh, look at that. So where's my shape maker?
There you go.
Boom.
Boom.
That's pretty good. Okay, well, anyways, so, you know, what we did here is we looked at this is the equation, has the equation x squared plus y squared equals 1. That's the x and the y axis. And what we did is we went a distance of t on the unit circle, and we identified t with that angle down there. And what we did was we defined x to be the cosine of t and y to be the sine of t. Okay. Now, back in 180, we learned how to do calculus with things like this that aren't functions. All of our approach to calculus has pretty much been through functions. Well, we used implicit differentiation to figure stuff out back then. Now we have another way of doing it, okay? So if this curve C is given this equation, x squared plus y squared equals 1, the assignment of x equaling cosine of t and y equaling the sine of t, where we'll let t run between 0 and 2 pi. This is what we call a parameterization of the circle. Okay. Now we can do this to lots of different curves, and we can even do it to functions. If I was to say, okay, here y is equal to x squared, and I started, you know, graphing it, okay, which direction is this graph going? Is it going left to right or right to left, or is it not specified?
I would say it's not specified, but if it was specified, I would say it's left to right.
And that's just because you grew up in the left to right reading place. Plenty of places around the world where they read right to left. Well, here's a way that we can do this and give it not only a direction, but a starting point. Like, let's say if we were to let x equal t, and then we'll let y equal t squared, and we'll have t run between -1, let's say, and 2. Then what we've done here is we figured out how to start it, and then it'll go up all the way up here to 4. That's not me with Parkinson's disease. That's this Apple pencil. Okay, and it goes that direction. All right. So by the way that we've parameterized the circle up here with x equal cosine t and y equal sine t, we're starting right here and we're going this way. Okay, well, what if you prefer to do something else? What if instead you would like to take our unit circle and start here and go clockwise? There's more than one way to do these things, okay? So x, y axis. All right, so the x is going to start at 0. So, and the y is going to start at -1. So maybe y can be the cosine of t, and that's not going to work. So come on, erase. How about if I let it be negative cosine of t? And I'm going to have t run between 0 and 2 pi. The x is going to have to start at 0, okay, and it's going to have to decrease. Okay, so if I put sine t right here, this is where it's a lot easier to be in the classroom because you can see me pointing at things and stuff. Then when t is equal to 0, x is 0, so I am right here. Still on eraser when I did that. So we're here and we want to go this direction. Okay, now as x increases, remember the sine curve, it's going to go like this. Okay, so the x is going to be growing positive. We need it to start at 0 and start growing negative. And so we can put a negative there, and that looks like we did the job. Okay? Now maybe you guys can come up with another way of perhaps doing that. Another standard example is the ellipse, x squared plus y squared over b squared equals 1. So just by kind of eyeballing it here, if we were to let x be a times the cosine of t, and we were to let y equal b times the sine of t, and let t run between 0 and 2 pi, then we see that x squared over a squared plus y squared over b squared is equal to 1. Okay, so I don't know if you guys remember how this works, but like, let's say that's a, and like, let's say that's b. That'd be negative a. That'd be negative b. The ellipse goes around like this. Okay. Now, very interesting thing happens when we try to calculate the arc length of this ellipse. So when we get there, after we end the normal part of the lecture at like 7:30 or so, then after that, I will get into that problem for the handful of you that might be interested in seeing where these bizarre things come from. Okay, so there we go. So let's see here. Let's see if we can, for example, figure out what curve they're talking about. Let's say that I've got x equals the square root of t, and y is equal to 1 minus t, as t starts at 0 and gets larger. So to eliminate the parameter here, what we would do is recognize that if you take x squared, you get t, and if you plug that in, you get y equals 1 minus x squared. And so what we got here is the upside down parabola. Okay. Now when t is 0, we're starting right here, right? Now the x will never decrease. So that means we have the parabola going like this, and we've given it a direction. The other side isn't there due to the way we parameterize this particular guy. Okay. And another one, let's see here. How about x equals 1/2 the cosine of theta, and y is equal to the sine 2 sine theta. I had to turn the light on and then it was too dark. Okay. Okay, so looks like if I want to take advantage of some stuff, I could say that 2x is equal to cosine of theta, and 1/2 of y equals the sine of theta. Now we do know that sine squared of theta plus cosine squared of theta equals 1. And so that means we would have 1/2 y squared plus 2x squared is equal to 1. And so this is going to be y squared over 2 plus 4x squared equals 1. And this, once again, is another ellipse. Okay. All right. There's an interesting one. Now, this is going to be a little rough for me to draw, but if we start with like,
Hey, Bobby, before we keep moving on, I just have a question for like a problem like that. What will we be given for the example, and what will the answer look like? Is it x equals square root of t is what we're going to be given off the bat, and the answer is y squared over 2 plus 4x squared equal 1? Or are there?
well, in this set of problems, it's asking you to figure out what the curve is. So
Okay.
all I'm doing is eliminating the parameter.
Okay.
Sometimes you can do this and sometimes you can't.
Okay.
So it just depends. All right.
Hmm.
Now let me tell you why we're doing this before I do
Okay.
another example. So eventually we're going to be looking at polar coordinates. We talked a little bit about that in pre-calc.
And in trig.
Okay.
Yep.
Yeah. And now in polar coordinates, when we have functions like, you know, r is some function of theta, when we graph these things in the XY grid, they're terribly not functions, you know, as far as X and Y goes, but they're perfectly good functions with R as f of theta, okay? So if we can somehow figure out a way to parameterize this guy, then we could look at this little piece right there. See that red piece?
Yeah.
Okay, now if that's all we were looking at, and that satisfies the definition of a function, doesn't it?
Yeah.
Yeah, implicitly, even though we can't explicitly write out what it is, implicitly it's there. And if we have a parameterization, which we will when we get to the polar stuff, then we'll be able to handle some stuff with it.
Are we going to be dealing with polar stuff like we did in trig, where it's like the cardiac and all the different ways they look?
Yeah, but we won't go as far as that goes.
Okay.
How do I make my shape again? What the hell's going on here? All right,
Click
so
the shape tool and drop it in, and then you can probably expand or contract it with your 2 fingers.
Okay, so here's my circle. Okay, now what's going to happen here is there's this point on the wheel that we're going to track. Okay, now this wheel is going to be rolling this direction. Okay, and we want to track this point. So imagine it's like a laser on this guy. So as this wheel rolls, what's going to happen here is that point is going to go up and then back down, then up and back down. You get that? Okay, so what we want to do is see if we can parameterize this curve. I know this is a very interesting one. It's
That's the one that looks like a butt, right?
now this is the famous Breccia problem.
Oh.
And this shape that we're drawing here is a cycloid. Okay, so imagine that this is the point P that we're trying to track. Okay, and I've tried to draw this so that if you roll this thing back this way, the P would roll right back onto the origin. Okay, now here's going to be the center of this circle. Okay, and we're going to suppose that it has a radius of an R. Okay, and so this is going to be an R right there. And this is the center. Okay, so we'll draw another perpendicular right here, and we'll call this point Q. Okay, like I said, this thing is rolling this way. Okay, well, there's an angle in here, theta, that we can play with. Blow this up so you can see it. Okay, so let's start working out some distances. So how far on the circle is it from the tangent point T to the point P? The arc from the point T to the point P, if you remember from your pre-calculus days, that's going to be R theta. Okay, that's how that works. Okay, and so this, if this is the origin right here, then the distance from the origin to T would then be the arc of that thing. So it's going to be R times theta. Okay. All
Is
right,
that
now,
is that an OT meaning origin or a theta T equals?
that's an origin.
Okay.
Maybe I should squiggly it. Okay, now this point right here has coordinates X and Y. Okay, and those are the ones that we're trying to figure out. Okay, so let's look at the X coordinate. The X coordinate is how far it is from C to T minus how far it is from, the X coordinate is how far it is from the, I was doing the Y coordinate. Okay, the X coordinate is how far it is from the origin to T. Okay, and then if we take away how far it is from P to Q, we're going to get this distance from here to there. Okay, so we already figured out that's R theta. And P to Q. Well, I know that the sine of theta would be P to Q over R. So that means that would be R sine theta. Now remember, the R is fixed. Okay.
This
far
is
as
probably a refresher, but real quick, could you explain one more time why the sine of theta is equal to P of PQ over R? I just can't
Sine of
remember.
theta is opposite over adjacent, opposite over hypotenuse. So
Okay.
this is the opposite side, the dashed line for that theta,
Okay.
and then over the R. As far as the y coordinate goes, okay, well, it's how far it is from C to T. And then if I take away how far it is from C to Q, we'd have it. Well, from C to T is R. And then C to Q, well, the cosine of theta is equal to how far it is to C to Q over R. So this would be minus R cosine theta. And so what we get is our final parameterization. The x is equal to R times theta minus sine theta. And the y is going to be the R times the 1 minus cosine theta. And if we started at 0 and run to 2 pi, we will have done 1 period of the cycloid, okay? All right, so the shape that this spits out of this curve is called a cycloid. All right. And it is a solution to a very famous problem. So way back in the days, even in the days of Galileo, okay, Galileo himself pondered this question. Suppose that you have a bead and you have some kind of a wire connected to the ground. And so this bead can slide on this wire, and I'm going to terminate right there. The question here is, what shape of the wire, what should the shape of the wire be so that the bead gets to the bottom in the fastest amount of time? Okay, so one way to, think about this is, well, shortest distance between 2 points is a straight line. But if you look at like this curve that's underneath it, the bead is going to get going a whole lot faster, right? And then this curve here, by the time the bead is here, it's really booking. Okay, well, Galileo, I haven't seen the math that he did to it, but he deduced that the shape of the wire should be a fourth of the arc of a circle. Okay, turns out that's incorrect. But later on, along came Isaac Newton, and he was able to solve it. Okay, and the shape of the wire, this is called the Breccia Kron problem. I don't know, it's a gnarly. Let me write it down.
The father of calculus, as you always like to tell us, right? Isaac Newton.
Yeah. He did a lot of good stuff, but invent and discover calculus is not one of them.
You said you saw that on what, Time Magazine or Newsweek or something like that? That was the one that you always tell us about?
No, I was waiting for a prescription at CVS, and I got the most Time Magazine's most influential people in history. And this included bad people too. I mean, you can't say that Joseph Stalin and Adolf Hitler were not influential. You know what I mean?
Yeah.
So, they made the list, and then here's Isaac Newton. I'm thinking, yeah, he should probably be in there. Then I'm reading about him. He invented calculus. No, he did not. So this is what's called the Brachistone Chrome. I don't even know how to pronounce it. Problem. And it turns out that the correct solution to this is the 1/2 of the arc of an inverted cycloid. Okay, so if you take half of, the cycloid like this, when it gets to its top, flip it and put it there, and that's the shape where the bead goes down the wire the fastest. So if it took like 2 seconds for the bead to get down from here, maybe it took 1.5 seconds for the bead on this middle one. This guy takes 1 second to go from here to there, and anything underneath it will be slower. Anything above it will also be slower. Okay, now here's something to ponder along with your navel. It turns out that if you put the bead anywhere on this curve and let it go, it's going to take 1 second. Even if you put it infinitesimally close to that spot, it's going to take 1 second. That's kind of interesting, don't you think? I mean, I thought so. Okay, so Galileo, like I said, he thought it was a circle. The Bernoullis were able to figure it out. Of course, Newton, he did it. And a Dutch physicist named Christian Huygens, of the famous thing that went to study the solar system, Saturn or Jupiter or whatever those one, he designed a clock, like a grandfather clock mechanism. You know how like you have a grandfather clock and the pendulum thing is going to swing back and forth? Well, if somebody runs by and hits the grandfather clock or whatever, it might be swinging too fast and it wouldn't set the right time. Okay, but if the pendulum was swinging along the arc of a cycloid, that it wouldn't affect it. And so this Huygens guy, he actually built one up like a little model thing, but you can obviously see how the time consuming it would be to do something like that. Okay, well, anyway, so that's kind of an interesting one. Now, if we just let the r equal 1, and we just stick with r equals 1, and we'll let x be this. I like to use t. I don't like using theta. Y equals 1 minus the cosine of t. If you graph this thing, it looks like this, doesn't it? Just keeps going. And you could even let it run backwards and it would keep going. Now, does this shape fit the definition of a function? What do you think?
Yes.
Yeah, it fits the definition of a function, the vertical line test, right? Okay, but if we try to do that and solve for it, we're going to see that we're going to run into some issues here. So let's see if we can eliminate a parameter here. Try to solve for y of x. Let's see, I guess we could say that the cosine of t is equal to y minus 1. So t is the cosine inverse of y minus 1. And x is going to be the t minus the sine of t. So that's going to be the cosine inverse of y minus 1 minus the sine of the cosine inverse of y minus 1. And so we can play around with the cosine inverse of y minus 1. It's equal to some angle. Okay. And so I don't know, complete the square thing. That squared, and then this is going to have to be what? Negative y squared. This is going to have to be 2y minus y squared. Because when I square this and square that and add it together, everything's going to cancel except that. And so the sine of that angle, then, as long as I'm not getting too carried away with my clumsiness, would be the square root of 2y minus y squared. Okay, but nevertheless, try to extract y out of that and you're not going to be able to do it. Okay, even though it's a perfectly good function, right? Okay, now I don't know all of your backgrounds. Some of you I do, but we've encountered a situation like this before. We had a function, we graphed it, it looked like this, and it was y equaling 2 to the x. We know it has an inverse because it's 1 to 1. We even know what it looks like because it reflects around the line y equals x. This is the graph of if f of x is 2 to the x, this is the graph of y equals f inverse of x. Okay, and then when we tried to go and solve for it, we found out that we couldn't do it. If you remember how this goes, you say that, okay, you switch x and y. So y equals 2 to the x equals 2 to the y. And you try to solve for y, and there's no algebraic thing to do. Yet, it's right here. I mean, you can't get more existent than that. If I drew it, it exists. Okay? But algebraically, we just can't find it. Well, so what we're going to have to do is call it something. So we call f inverse the logarithm base 2 of x. Now, in my stack of math journals that I brought home from the lounge in NBCC, whatever, there's a article in one of them that caught my eye on what Napier's logarithms. Napier's the guy that invented logarithms. His logarithms are a bit different than the ones that we use. So, plug my mouse. Okay. Where's the hell pencil? Okay. All right. So if this shape up here, this cycloid shape was so important, then maybe we would give it a name. But because we can parameterize it like this, we generally don't. If we could have parameterized somehow this guy, we would have. But I've never seen any show up. Okay, so obviously what we now want to do is some calculus. Okay, so if we're given like a curve C, which is given by x equaling x of t, y equaling y of t. Now your book likes to use f and g and stuff like that. I just like to use x as x of t, okay? It may be the case that we're parameterizing stuff that looks like this, where it might go like this, and like this, and around, okay? Now, even though this curve is intersecting itself and all of that stuff, what I tried to attempt to draw was a curve that had a well-defined tangent line everywhere, okay? Now, remember that we're graphing this in the XY grid, okay? So what we want to do is find dy dx from x of t and y of t. Okay. All right. Well, we have got that y is a function of t. And implicitly, y is a function of x. Implicitly. Okay. Like if we just took and looked at the piece that runs from here to here, that's a function. We can figure out dy dt, and we can throw in a little chain rule step by saying, well, since I want to get x involved in this, this would be dy dx times dx dt. This is the chain rule step, implicit chain rule step. And so what we find here is that dy dx, which is the slope of the tangent line, is equal to dy dt divided by dx dt. All right. Okay, so let's see what this is going to give us. Let's say we're doing the circle, so x is going to be the cosine of t, and y is going to be the sine of t. Now, we've solved this implicitly, and I think the answer is negative y over x or something like that, okay? But we'll just do it from this. dy dx is going to be this y dot divided by x dot. Okay, so I'm going to start using this Newtonian stuff. So for you guys that are going to sample some more physics, anytime you're taking the derivative with respect to a parameter, that's usually when you're going to see the dot notation. Okay, so y dot is cosine of t, x dot is sine of t, negative, okay? And so it's negative cosine of t over the sine of t. And notice that that agrees with what we got when we did it implicitly. Okay. And so if let's say we want to find all points where the slope of the tangent line is undefined, we just look at, okay, dy dx is negative cosine t over sine of t. Okay. And this is going to, if sine of t is equal to 0, we have a problem. And that's going to occur at 0 and at pi and at 2 pi. So that's where that would happen. We go back to our other guy, our cardioid, our cycloid issue. Remember, it does this, okay? Now, these pieces are occurring at 2 pi and then at 4 pi and at 0 as well, okay? That looks like a cusp to me. So I don't think that this guy is going to be differentiable at those spots. The only way to do it is to do it, okay? So x is going to be t minus sine of t, and y is going to be 1 minus the cosine of t. Y dy dx is y dot divided by x dot. So y dot is the sine of t, and the x dot is 1 minus the cosine of t. Okay, so when does the cosine of t equal 1? 0, 2 pi, 4 pi. That's exactly what we thought. Okay. Give you a second here. Okay. So let's see here. Let's see if we can find the second derivative now. Remember that the second derivative gives us acceleration. It also measures, tells us when you're concave up or concave down. So this might be important. Okay, now I want you to, for the cycloid, above, I want us to compute y double dot over x double dot. Okay, so that's going to be the cosine of t divided by the sine of t. Okay, now that's the cotangent of t, right? And when we're in the first quadrant, like if t is between 0 and pi over 2, the cotangent of t is positive. Okay, now, if this thing was going to be our candidate for the second derivative, then it would have to mathematically predict everything that it needs to predict. One of the things that we can say about the cycloid is that it is concave down for all values of t. That means that d squared y dx squared is negative, right? The derivative function dy dx is changing from positives to negatives, so that means it's decreasing, so that means it's got to be negative. Okay, so this cannot be d squared y dx squared. In order for us to find it, we're going to kind of do a little sleight of hand. Excuse me. Okay. Oh, where's that guy? Okay, so if I was to look at d squared y dx squared, okay, and when you get next semester, you know, do yourself a favor and don't take the time off between these two classes. You know, go back and keep integrating and take derivatives. Okay, so dy, the second derivative, is the derivative with respect to x of dy dx. Okay. So now the derivative with respect to x of y is going to be the derivative with respect to t of y divided by the derivative with respect to t of x. Okay, now I'm using different notation here, and if you start getting confused, keep in mind that so I had a student a couple years ago, this guy Frank, and got an A, good student. He never understood this concept of d by t of y. Okay. All right, so what we're going to do here is this trick, is we're going to replace y with dy dx. Okay, so that means that what we have done here, dy dx, is equal to the derivative with respect to t of dy dx divided by the derivative with respect to x of t. There is nothing to do there. Okay, and so what we get is that dy dx is going to be dy dt divided by dx dt, and the second derivative is equal to the derivative with respect to t of the thing you found divided by dx dt. Okay, and so these are the things that you're going to want to remember. Now, this first one you'll probably know because you're going to use it all the time. By the time we're halfway through Math 280, you're probably not going to remember this second one, and you're just going to have to re-look it up, okay? But for people that are dealing in second derivatives all the time, you know, orbital mechanics and stuff like that, you know, maybe they have that committed to memory, okay? All right, so let's do the cycloid. For our cycloid, the x was equal to, what is it? It's t minus sine t and the y is the 1 minus the cosine of t. Well, minus or 1 plus. Yeah. Okay. Okay, so we already know what dy dx is. So it's y dot divided by x dot. Okay, so the second derivative, d squared y dx squared, is the derivative with respect to t of this mess divided by dx dt, which is 1 minus cosine of t. Okay. All right, so let me write this 1 over 1 minus cosine of t out in the front. And then it's going to be the derivative of the top, cosine of t, times the bottom, minus the derivative of the bottom, which is plus sine t, times the top, all divided by the bottom squared. Okay. And this is, I lost a negative. It's the derivative of the top times the bottom minus the derivative of the bottom. Well, the derivative of the bottom is positive, so it's going to have to be that. Okay, so now I'll clean it up a little bit. This is going to be cosine of t minus cosine squared of t minus sine squared of t divided by 1 minus cosine of t cubed. And that's equal to the cosine of t minus 1 over 1 minus cosine t cubed. And then for you algebraically challenged people, I won't skip this step. I pull a negative out of that. Okay, to finally give us our final answer, the second derivative is equal to negative 1 over 1 minus cosine of t squared. The denominator is always positive, the numerator is always negative, so this is going to be negative for all t, meaning it's concave down, just as we had suspected. Okay. All right. So I guess now, depending on what book you're using, he is going to cram all of the stuff into one section, like he's doing here in 10.2 in version number 7, edition 7, or he's going to spread it out. So instead
A lot of
talking,
us have the 5th edition.
okay, so I'm just going to look at, and a lot of you have PDFs of the online version. So I'm just going to do these in order, but this is all in chapter 10. It's in these first few sections, okay? So the first thing we did is we figured out that slope of tangent line and that next problem. Next thing we do with calculus is we look at area. Okay, now this doesn't always work. Okay, meaning that, you know, if I have a curve given by y equals a function of x, where f of x is positive on an interval, let's say a to b, we learn that the area between the function and the x-axis is this. Okay, now this is going to be a sleight of hand, okay? Imagine I was going to be doing a trig substitution, okay? So the y is going to be some function of t, and the x is going to be some function of t. Okay, so when we were doing trig substitution, you know, we would say x equals either the sine of theta or the tangent of theta, sometimes the secant of theta, and then dx equals accordingly, okay? So what I'm going to do here is I'm going to do this all symbolically, okay? So now the bounds, this is when x is equal to a and x is equal to b, okay? So when x equals b, that might occur when the parameter is maybe a beta, and x equals a might occur when the parameter is alpha. Okay, so if we did the trig substitution, we would plug it in here and we would say, okay, well, now I'm going to go from alpha to beta. And then whatever the y is, because remember the y is the f of x thing. Now we're have it now in terms of t. And then in order to do this, we would do dx dt times dt. Okay. And so this is the formula that we end up using. Okay, now your book is using something stupid. He's using F and G, get away from that. Y of t, x dot of t dt. Okay, now this is only when this concept of area makes sense to talk about. Okay, it might be that we parameterized a curve that does this. So what's the area under the curve between here and here? You know, it's like, what, you know, am I subtracting this area off after I already included it? You know, so you get some real whack answers. So hardly anybody uses this stuff, but let's experiment. So let's say that I've got the top half of the circle. So y equals 1 minus x squared. Okay. So this is what I've got, this part. Okay, so if we parameterize it by x is equal to cosine of t and y is equal to the sine of t, and instead of going all the way around, I'm just going to go to pi. Let's see what ends up happening. So our formula for the area would be from 0 to pi, then it's y sine t, and then dx dt, which is negative sine t dt. Okay, now next semester when we're doing line integrals and stuff like that, you will get very used to doing these kinds of computations. So set yourself up for the future and do a bunch of these on your own. Don't just, you know, watch me do them. So 0 to pi of negative sine squared of t. Okay, and we know how to handle that. 0 to pi, negative 1/2 minus 1/2 cosine of 2t. And you know me, I don't like to waste an opportunity to get rid of a negative. So I'll go from 0 to pi, 1/2 cosine of 2t minus 1/2. Okay, so now we integrate. Sine of 2t over 4 minus 1/2 of t evaluated at 0 and pi. Well, the sine of 0 and the sine of 2 pi are 0, so that goes. So what I'm getting is negative pi over 2. Okay, somebody tell me what's wrong with that answer.
The negative pi?
Negative, right? The area is positive. And we know what the area is. It's pi over 2. Why are we getting negative? God hates us?
We use the negative sine t.
Is that what it is?
Yeah, if we would have done the sine squared t dt, it would have probably come out positive.
Well, we know the culprit is this negative, right?
Yeah, right.
Is the negative one of Bobby's brain parts, or is that okay?
It's okay, but I mean, we're talking about
Okay, so we've got a dilemma that we've got to resolve here. All right, anybody care to try to resolve it?
Yes, we use the cosecant.
No, it's kind of subtle.
What
It
if
has
you
to-
bring the negative out of the integral?
Okay, so it's actually a very basic answer. The reason is we use the parameterization x equals cosine of t and y equals sine of t. And we let t go from 0 to pi. So what happened is we traveled on this curve, this direction. So that meant our delta x was negative, even though delta x is never up in the picture, okay? So the correct way to do this, and see, this is why hardly anybody ever computes area using these things, because for this one, it's screamingly obvious. But for other curves, it might very well be that it went negative just for a little bit and then went back to positive. And you get an answer that you would buy. It needs to be a positive, but it's not the correct positive. Okay, so the correct thing for us to do here, if we want to do this with parametric equations, is go this direction. What's wrong with this pen? Go.
So instead of going from 0 to pi to 0, we're going 0 to pi.
Well, what I'm going to do is I'm going to reparameterize the curve that goes the right way.
Oh,
Okay, so x is going to be something. The y is going to start at 0 and increase. Okay, the x is going to start at -1 and decrease to 0. So if I put negative cosine t here, cosine t starts at 1. I don't need, right? And so I put negatives in front of all these, and it looks like I got it. Okay, so now if I integrate from 0 to pi, y dx, it's going to be 0 to pi, y dx dt, dt. Depending on what semester it is and who you guys are, some people have real issues with that step. And other people just, you know, accept what it is. Okay, so now let's fill it all in. So it's going to be, of course, I keep going back to the dumb thing. 0 to pi, then the y, which was the sine t, then dx dt, which is going to be the sine of t. So notice that that sine t goes on. And now we know that this answer is going to be pi over 2. Okay. All right. Now, the next thing that we're going to tackle is arc length. And I'm going to save that for tomorrow. I learned my lesson last semester. When I'm not up in front of you, I can't just keep going and going and going, because, you know, I understand all this stuff. But for many of you, this is the first time you're seeing it. So find a bunch of homework exercises if you can. Oops, plug my guy back in. Okay. And get my mouse back out. Stupid thing in. All right, so I'm curious to know, what did you guys use to do the test? Like, how did you figure this out? Was it the old fashioned, just your roll up your sleeves and do it yourself, or did you like start looking in places and stuff like that?
For 7, I looked up like if a hint, like, where do I start off from, and then I just gave up, and then I started working through it because the example that we're playing through didn't match up to what we learned in class, and I didn't find an example. I had to go back through my notes to see something. That it was like, basically, it was basically finding out you can do the power rule to turn it into du and use u, and then do a substitution from u to x at the end.
Yeah, now the one that I did for you guys last semester, it was cube root of x plus square root of x.
Root of x plus square. Yeah, I might have like lost it when, so sometimes when you would tell us Calc 2 stuff in Calc 1, I sometimes would stop copying at that point. So I was wondering, I tried looking through my whole notes, but I missed it.
Oh boy.
Yeah, it wasn't in this notebook. I have to look for the other notebook.
If you're gonna be hanging out with Bobby, you probably need to. I mean, I'll reference stuff. Well, anyways, so I knew it was out there. So instead of doing that problem, I wanted to throw one on I didn't do. I know I wouldn't have done this one on the board. That would take too long. You know, it took me 5 minutes to do it. Basically, I got home from Murrieta today, and I had done, or Menifee, place is an armpit, man.
I've been for my drafting job. It's no good.
Yeah, so I did number 7 last night, and then I just did all the problems right before my wife worked out. So there you go. So be kind of interesting to see, you know, what you guys came up with. Okay, now don't get all worked up and bent out of shape if you missed a bunch of these things. You know, I'm trying to treat it like it's a normal class where you would have written down a bunch of work and I would have given you partial credit for your work and all that stuff. Okay. There's certain things I know you can look up. These integrals though, I mean, I had that Hewlett-Packard calculator that could take derivatives, and my TI-80 whatever calculator can numerically integrate stuff. But as far as like where to look for this kind of stuff, you know. Okay, another observation I made on the test was number 8. So did you guys multiply the top and bottom by the square root of 1 plus cosine x? Was that the most popular thing done?
I believe so.
Okay.
I mean,
There's another way you can do that problem. You can say that 1 minus sine x, 1 minus cosine x is 2 times the sine squared of x over 2.
Yeah,
Use
you
that
did this
Yeah,
in class earlier.
right. And so that answer is going to involve the cosine of x over 2 when it's all said and done. Because it's gonna be negative it's negative
it was negative 2 radical 2.
negative, yeah, negative 2 radical 2 cosine of x over 2, right?
2 plus c, yeah, plus.
So evidently that's an identity. So yet another interesting thing to do while you're watching what marathon is on tonight here. It was Parks and Rec earlier. It's on that one channel.
That one was actually in the examples for the identities in the book.
Ooh, Monty Python and the Holy Grail. I give you these 15, crash. These 10 commandments.
Such a dumb movie.
That movie's awesome.
I've been watching this speaking of like dumb movies, I actually have it here. I've been watching it on Soap today. Have you guys ever seen this movie?
Oh, it's incredible, man. Have you watched
It's
Waiting
hysterical.
for Guffman?
Oh, I watched them all.
Okay,
This
yeah,
is
that
my
guy's
favorite.
Christopher Guest. He's incredible, dude.
This is my favorite one though.
Even more than I think Waiting for Guffman's still my favorite, but Mighty Wind is probably. I mean, I've seen Best in Show too many times, but that one, those three are like the best. I think.
I mean, Fred Willard is just so funny.
Yeah, it's.
And let
like,
me ask you this: with the bigger dogs, does any of the trainers come in riding on the back? You know.
Oh man. Oh,
And those songs.
movie. Oh yeah.
There's been a mighty hymn. I'm the cabin boy, call me Jim. And then he goes,
They
his
did
name's
the
Jim.
O's, like the Eat at Joe's is their final thing that they did because they made it big.
Well, they don't allow no frowns inside. Leave them at the door. You can tell I've been watching this movie.
Yeah. Yeah, I haven't seen that one forever. They don't have it streaming anywhere, and
Soap today.
What?
Okay, so if you go to this, let me put it in the chat. So it's Soap today dot, and then there's a bunch of them. TO, whatever.
Oh, I heard that out.
Okay, now you probably want to do it on an Apple because
Yeah.
there's a virus that's in it and stuff, and Apple is unhackable. Okay.
You also probably want to have a VPN though, man. Like I have one, so I've gotten quite a few of those. But I'm just meaning the quality's not always going to be good though. That you're getting.
It's been pretty good. I've been watching this.
Okay.
So yeah, I've like that one, and I think, what do I have tonight? There's some Mayan, Lost Cities of the Mayan, I don't know, something. I think tonight I'm going to watch something to make my brain work.
Did you watch the McMillions show real quick? Did you watch
Which
that
one?
one? McMillions. Yeah, the idea like that the
Is that a movie?
No, it's like a HBO like documentary about the McDonald's like fraudulent monopoly game that happened that was all like set up, and that like one person won every time, and then yeah, anyways, it's crazy. It was about you remember the McDonald's Monopoly game that they used to play?
Of course. So that was my freshman year in college, and we kept going to the same McDonald's. You couldn't get Boardwalk. That was
You
the
could
hard
win. They actually like literally they proven here like anything above, I think it was like $2,000 was essentially stolen by this one like family who worked as a security guard at the center where they made the pieces. That's according to.
Okay, well, what happened? So my roommate, my friend Pat and whatever, we're living in the dorms, and we go up to the drive-through at McDonald's, and the girls that are working at the window, they kind of like have a little crush on us or something like that. So we're always asking for more game pieces. So this one night, the girl, she took this box out that was about the size of like maybe 3 large shoe boxes, and just gave us all of them. We had probably a couple thousand of these things, and we went through all of them, and we got a whole bunch of free food, but we didn't get any we didn't get the Boardwalk.
That's the one you need for actual prizes, right?
Yeah.
Or like money.
It was back in 1987 or 1988, whenever that
It's been
was.
a long time. The 90s was the last time I remember it, man. I don't know if they played it after.
They did play it again in the 90s, I do remember.
Yeah.
They had it again in the 2000s where they had the whole board, but it wasn't like as big as the original one.
Oh, okay.
The 90s, yeah.
Well, anyways, they proved that all of that was just like fake. I thought at first McDonald's was just doing it fraudulently, but so according to this documentary, they say a security guard who worked at the warehouse essentially took all of the winning pieces. So he like won. Sorry, not trying to spoil the documentary, but it's interesting. So
Another thing I'm recognizing on the test here is there's going to be a couple different ways to do number 9. I did partial fractions on it, but there are going to be some, you can do it with trig substitution, and you can also do it with hyperbolic substitution. Okay, and so if you remember those bizarre identities that we had with the hyperbolics and the logs, again, you know, when you're looking for more stuff to do, just keep doing it. Okay, so what I'd like you to be doing now is a lot of those problems with arc length, as many of those as you can, okay? Because tomorrow we're going to start off with arc length. We're going to be talking about parametric equations and how to compute the arc length. And from there, we will probably look at our first elliptic function. So, and that'll be for like this time in the class, where the only people that like be a little extra. It wouldn't test you on it or anything, but it's important because, especially in these times right now, what I'm recognizing, have any of you like been using software like Mathematica or things like that to evaluate these integrals? No? Okay.
I mean, there's free stuff online.
Okay, so there's a I had a student years ago, and this was back when they were redoing the Lewis Center and I was in the temporary office, and he kept coming in. He was saying, well, now I'm trying to do these problems. He was a real hard charger. You know, he was doing you know, other stuff out of other books, and he was using this Mathematica or Maple or something like that. And anyways, he would type these things in and it would say error, elliptic integral type 1, error, elliptic integral type 2. So I want to, at least for the handful of you that are trying to learn some stuff here, I definitely want to go through that and show you what that all means. Okay. I think some of it was stolen out of my truck. I'm trying to figure out where I put that master file of stuff that I had, but, and anyways, that'll be for tomorrow. And looks like, are we having a sleepover at my house? I hope not.
Well, good luck, man. I'll see you tomorrow.
Yeah. Okay, now, just as always, if you run into something, take a picture, send it to me, and I'll bang it out real quick and send it back, okay?
All right, cool. Thanks.
All right, everyone. Stay classy, San Diego.